Young was a great material scientist, after whom an indicator of the overall properties of a material when exposed to force was named. The Young modulus gives a general indication as to the nature of a material and how it behaves when exposed to forces. A high Young modulus means that a material will not extend much when exposed to forces. These materials tend to be brittle. A low Young modulus means that a material will extend greatly when exposed to force. A negative Young modulus means that removing force makes a material expand. A positive value means that expansion is caused by application of force. The Young modulus of a material changes depending on the force applied to that material, but is a good general indicator of the general properties of a material under most circumstances. The Young modulus is the ratio of stress to strain on a material. In this way, it is the gradient of a stress-strain graph. It can be calculated as the gradient from a stress-strain graph, or mathematically as stress divided by strain. Stress is force over area, and strain is extension divided by length. Combining these equations together gives us Young's modulus as force times length divided by area divided by change in length. In order to measure the Young's modulus, you must measure the stress and the strain of a material when subjected to a force. Stress is measured as a force applied to a material, divided by the area over which it is applied. You can use scales to find the mass in kilograms of a weight you are applying, and multiply this by 9.81 to find the force applied to a material. Or you can use a Newton meter, using Hooke's law's principles of a spring with known Hooke's constant to calculate the force you are applying. The interesting aspect of stress is how to measure the cross-sectional area of the force is applied over. To measure this, you must use a distance measuring device. At large scales and low accuracy, a simple ruler will do this. As Young's modulus is usually calculated on strings of material and then multiplied to give a bulk value, this is impractical. A ruler does not have the accuracy. Instead, you must use vernier calipers, or more commonly, a screw gauge micrometer. Both of these devices use a vernier scale, so that you can see very small values of a reading and read them with your own eyes. Where two lines of a vernier scale are lined up, this represents the value on the vernier scale. You find where two lines are lined up, and you take your reading from there. Vernier calipers work by pressing two prongs together either side of a string, or moving the two prongs apart to measure a gap. You judge when the calipers are just touching the material. A screw gauge micrometer, however, uses a ratcheted screw to stop closing when a certain level of resistance is met, making it far superior when measuring thicknesses. Either method requires multiple measurements of diameter to be measured for a wire, and then the cross-sectional area can be calculated using the diameter divided by 2 squared and then multiplied by pi. By averaging the value over a distance of the material, you can give an accurate value of the cross-sectional area of a material, and therefore a good value of the stress. The strain requires vernier calipers, as the extension of most materials is very low when exposed to force, and you require a very sensitive measuring equipment to measure it. Typically, you would put a mark on a non-stretching material, so you can compare a start and an end point of a stretching material, and measure this distance using vernier calipers.